What's up, everybody? In this video, we're going to be covering USACO's 2022 February contest at the bronze level, problem number 1, sleeping in class. Bessie the cow was excited to return to in-person learning. Unfortunately, her instructor, Farmer John, is a very boring lecturer, and so she ends up falling asleep in class often. Farmer John has noticed that Bessie has not been paying attention in class. He has asked another student in class, Elsie, to keep track of the number of times Bessie falls asleep in a given class. There are n class periods, where n is between 1 and 10 to the 5th. And Elsie logs that Bessie falls asleep AI times, where the number of times she falls asleep is between 0 and 10 to the 6th in the ith class period. So basically, we've got some number of class periods like period 1, period 2, period 3, period 4. For each one of those time periods, the number of times she falls asleep represents AI. So, for example, A1 is the number of times she fell asleep in class 1. A2 is the number of times she fell asleep in class 2. The total number of times Bessie falls asleep across all class periods is at most 10 to the 6th. So A1 plus A2 plus A3 and so forth is going to add up to at most 10 to the 6th, which is 1 and then 1, 2, 3, 4, 5, 6. So at most a million times. Elsie, feeling very competitive with Bessie, wants to make Farmer John feel like Bessie is consistently falling asleep the same number of times in every class, making it appear that the issue is entirely Bessie's fault, with no dependence on Farmer John's sometimes boring lectures. The only way Elsie may modify the log is by combining two adjacent class periods. For example, if A was equal to 1, 2, 3, 4, 5, A again being the number of times she fell asleep. So this would be 1 time falling asleep in the first period, 2 times falling asleep in the second period, 3 times in the third, and so forth. Then if Elsie were to combine the second and third class period, which would be the 2 and the 3, the log will become 1, 5, 4, 5, right? Because 2 plus 3 is going to be 5, then we'll have 1, and then 5, 4, 5, and the list of numbers gets shorter as you combine them. So that makes sense. Help Elsie compute the minimum number of modifications to the log that she needs to make so that she can make all the numbers in the log equal. Okay, so we have to change the log by combining neighbors and try to figure out how many combinations we need to make in order to make it so that all the numbers are the same. So in the case of like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, trying to combine neighbors to make everything equal, this case I don't think is going to be possible because I've got a 5 here. I could combine the 3 and the 4 and have 7, but I can't turn 5 into 7. And if I were to combine the 4 and the 5, then that would be 9, and I have no way to turn 1, 2, and 3 into 9. So some of these are going to be possible, and some of them are going to be impossible. Let's see. So the input format comes from the terminal, from standard in, so just typed into the console. Each input will contain t-test cases that should be solved independently. You've probably seen these on a couple of the more recent problems. Basically what that means is instead of being an individual test case, each test case has subcases. So like this is a test case, this is a test case, this is a test case, and this is the number of test cases there are. There's some good strategies for dealing with this, but basically usually what you want to do is read that first number of test cases in, and then just call some function that many times. And that function should read the n as well as the values. Anyway, as much as possible as you can try and turn this into solving individual problems and then not have to worry about the test case is probably a good idea. Okay, so first contains t-test cases should be solved independently. First line contains t, the number of test cases to be solved. The t-test cases follow. Each described by a pair of lines. The first line of each pair contains n, so that's like n, and then this also is n, and then this also is n. But for each individual test case, these are kind of separate cases. And the second line contains A1, A2 up through AN. So then this is like the number of times that Bessie fell asleep during this particular test case. It is guaranteed that within each test case, the sum of all values in A is at most 10 to the 6th. They mentioned that a couple times. Since they're mentioning that twice, it usually means it's a big hint. It's also guaranteed that the sum of n over all test cases is at most 10 to the 5th. Okay, so we have at most 10 to the 5th n, which is this 6, 3, and 5. Basically, what they're letting you know is we could potentially have only one test case, where then n could be 10 to the 5th, and then the sum of all these would be at most 10 to the 6th, or we could have individual test cases. And they're just letting us know that as we have multiple test cases, it shouldn't impact our time complexity. If we can solve it within a time complexity that handles 10 to the 5th periods, and then have 10 to the 5th numbers, that add up to at most 10 to the sixth, then it should work for all the examples. Output format is T lines of output. So basically we have a line of output for every test case, giving the minimum number of modifications LC could perform to make all log entries equal for each case. Okay, let's go down a little bit further. So actually we have an explanation at the bottom. Start from here. Okay, so 3 test cases. First one is 6 numbers, and those 6 periods for class, and those numbers are 1, 2, 3, 1, 1, 1. So it says then the sample output for that is 3, which means we can make these numbers all the same in 3 modifications. For the first test case in this example, Elsie can change her log to consist solely of 3s with 3 modifications. First modification looks like it's combining the 1 and the 2 into a 3. So I'll have 3, 3, 1, 1, 1. Second modification is combining these pair of 1s. So I'll have 3, 3, 2, 1. And third modification is going to be combining the 2, 1. So I'll have 3, 3, 3. Oops, too many bumps on that 3. Anyway, so combining the 1 and 2, combining the 1 and 1, combining the 2 and the 1 gives us 3, 3, 3. And that's then 3 operations to get them all to be equal to each other. For the second test case, Elsie can change her log to 7 with 2 modifications. Okay, so this is 2, 2, 3. This is a good example. So if we need to make all the numbers the same, then we would have to combine these 2 to make it 4, 3, and then these 2 to make it 7. So actually earlier, the test case that had 1, 2, 3, 4, 5 does have a solution, and the solution is to combine all of the numbers, which would be 1 combination to make 3, 3, 4, 5, 2 combinations to make 6, 4, 5, 3 combinations to go 10, 5, and then a final combination to make 15. So everything is solvable with some number of modifications. For the last test case, Elsie doesn't need to perform any operations, so the log already consists of equal entities. Right, okay, so these are all zeros. So this is just pointing out that it's possible for them all to be zeros. And in addition, if they start out all the same, then there should be 0 modifications. All right, so the question then is, how do we try and figure out what number to sort of try and target as we work our way towards figuring out whether or not there's a way to combine all these numbers? For example, if I start with this first one and I have 1, 2, 3, 1, 1, 1, if I knew that the target was 3, then it'd be quite easy because I see 1 is less than 3, so I must combine it. Next number would be 2. I would combine them and get 3. And now that it's 3, I could move on. Next number is already 3, so I can leave it alone. Next number is a 1, which means it must be combined with the 1, giving us 2. But 2 still isn't 3, so it must be combined with the next one, giving us 3. If we knew that 3 was the target, but we don't know that 3 is the target. We don't know what our target is. I recommend taking some time with a pencil paper and fiddle around with this. Try a couple different number combinations just at random, and see if you can think of some way that you can approach trying to solve this in an efficient way. We don't have to be too terribly efficient because we only have 10 to the 5th numbers, but we do need to be a little bit clever about what numbers we're trying to solve for. I'm going to try and come up with a number combination for us to do here. Let's do this. All right. All right, so if you've had a chance to play with this, we'll move forward and try to explain this algorithm. So one thing I mentioned earlier is that if you knew what the number target was, then it's not that hard to see whether or not your numbers can add up to the target. So for example, let's say like I knew my number target was 7, or I'm going to test the number target 7 to see whether or not it's even possible. So I start from the first number, 4. 4 is less than 7, so it must be combined with its neighbor. So we'd have 4 plus 2, which would be 6, but 6 is still not 7, so I must combine with the next neighbor. Next neighbor is 3, which equals 9, which means 7 cannot possibly be the value that everything will be equal to, because ultimately we're supposed to make all these numbers equal, but we can't make them all equal to 7. And we know that because starting from the beginning here with the 4 on the edge, the only thing 4 has a choice to combine with is its immediate neighbor. And the only thing that can combine with, if it's not enough, is the immediate neighbor. And if we overshoot our target, that means there's no way to make everything equal to that number because we can't make the first number equal to that number. Let's try 8. So if I want to try 8 as a target, I would have 4. I'm going to add 2, which gives me 6. I'm going to add 3, which gives me 9. Can't make an 8. Let's try making a 9 because we already know we can do that. So let's say I combine these guys and I get a 9. I then have a 1, must combine with a 2 to make 3, combines with a 4, which makes 7, combines with a 1 and combines with a 1, which is 8 and then 9. So I could make them all 9s. Now, if I know that I can make them all 9s, then I would need to know how many operations that would take. Now, since every operation is combining 2 neighbors, then I know that if this is my starting set, which is 1, 2, 3, 4, 5, 6, 7, if I started with 8 numbers and I ended with 2 numbers, then I must have combined 6 things. I combined the 4 and the 2. I combined the 6 and the 3. That was 2 combinations. I combined the 1 and the 2. I combined the 3 and the 4. I combined the 7 and the 1. And then I combined the 8 and the 1. So I have 1, 2, 3, 4, 5, 6 total combinations. And that makes sense because 6 combinations would take 8 numbers down to 2. But the question isn't, is there any way to do it? The question is, what is the fewest number to do it? And is this the smallest number? So what we're looking for is we're trying to find the smallest target number. In this case, 9 is our target number. We're trying to find the smallest possible target number where I can add numbers up and have them all equal to that number. So testing out target numbers, we probably should start from a low value. 0. Is there any way to get it to add up to 0? No, obviously, because 4 is already more than 0. Could you make all the numbers equal to 1? Also no. Could you make them all equal to 2? Also no, because I've got 4s. Can't make them all equal to 3. 4 is the first number that's even worth trying, because I should be able to make them, or I won't be able to make them less than whatever the largest number is. Because if I'm going to combine numbers and get them all to be equal, I can't combine a 4 with anything and have it be equal to 3 unless there are negative numbers, and there's no negative numbers. So assuming 4 is our first reasonable target to shoot for, we can run through and see, okay, well, 4 is already 4, and then 2 would have to combine with 3, but 2 combined with 3 is 5. That's too large, so 4 is not going to work. What about 5? So if I were to try 5, I can do 4 and combine with 2, and that's going to be 6. Oops, and that's still too much. So that's not right. Now, this will work, but the problem with that approach is the total, let's see, let me pull up this is one of the only problems that I've run across in bronze where you have to really, really be very careful about your time complexity. The reason why this is a potential issue is I've got 10 to the 6th, 10 to the 6th potential times that Bessie has fallen asleep, which means potentially I have 10 to the 6th different numbers I might need to try. And there are, or sorry, that's 10 to the 6th times she fell asleep. It's 10 to the 5th. Yeah. So 10 to the 5th total class periods, which means I have 10 to the 5th total numbers. And then to combine them, I have 10 to the 6th total potential times that she fell asleep, which means there's 10 to the 6th total possible numbers that these could be equal to when they're all combined. And the problem is if I try every single possible number, and then for every single possible number, I have to run through n, then I'm going to have potentially 10 to the 6th times 10 to the 5th. Because I've got 10 to the 6th numbers to test for a target, and it takes 10 to the 5th, there are 10 to the 5th numbers that I have to run through and test. So I will do 10 to the 5th operations 10 to the 6th times, which is 10 to the 11th. Now 10 to the 11th is too large. In fact, 10 to the 10th is too large for most of these USACO problems. I think there have been like maybe 1 or 2 problems where they extended the runtime limitations. But for the most part, if you have a 10 to the 10th, you're going to go too slow. So that would be considered a brute force solution, would be trying every single number. So what we need to do is we need to try and figure out a way to make one of these numbers smaller, either the 10 to the 6th or to the 10 to the 5th. So our approach is pretty good so far. We've got a linear way that we can run through, and we can verify whether or not it's possible for all of these numbers to add up to a certain target. And just to kind of recap that, whatever your target is, if your target is equal to 4, for example, then what you're doing is you're checking each index. If it's equal to 4, then you move on. If it's not equal to 4, you start making a running total. And you start adding numbers. So here's 2, and then here's 3. If at any point this running total is equal to 4, you can start it back over at 0. But if at any point this running total goes over 4, that means it's not possible to combine neighbors in order to make our target number. So we've got a linear verification here. The thing we need to do is figure out how to reduce the number of numbers we have to test. And we don't really see that being a problem with these because this is just a short list with small numbers. But when these get to be much longer lists with much larger numbers, our target could be in the tens of thousands. Maybe our target is like 150,000, for example. And if we have to try 2 and then 3 and then 4 and then 5 and then 6 and then 7 all the way up to 150,000, and we have to add potentially, 100,000 numbers together in order to try and reach this target, it's too much work. But we can have a really quick check to see whether or not a number is not a viable total. And this quick check will involve adding all these numbers together. Because if you think about it, no matter what your result is, by combining numbers, you're not going to change the total number of times that Bessie has fallen asleep. So you got 4 plus 2 is 6. Actually, I totaled earlier they could be 9 and 9, so it's going to be 18. I'll have to add those up. So if I have 18 as a maximum, then what that means is that if all these numbers are to be equal, if I'm going to do some amount of combination to come up with some number of numbers that are all equal to each other, equal, however many of those numbers there are, they still have to add up to 18. So if I was to have 2 numbers, they would have to be 9 and 9. If I was to have 3 numbers, then they would have to be 6, 6, and 6. If there was to be 4 numbers, then I can't do it because 18 is not divisible by 4. So what you can do is, as you're testing out numbers, you can check to see whether or not your target is even divisible by that value. If I want these numbers to add up so that every target is 4, and we already verified that didn't work because the 2 and 3 doesn't add up to 4. But without even having to do that check, I can check to see if 18 modulus 4 is equal to 0. And if it's not, then there's no reason to try and have a target of 4. Because what that would mean is if my target was 4, then that would mean that I would have to have 4 here, add up to 4 here, 4 here, 4 here, 4 here. But then that's not going to be 18, that'd be 16. And if I have another one, then that would be 20, and I don't have enough. I only have 18 to do that. So I don't have to test the number 4. I also don't have to test the number 5 because 18 is not divisible by 5 either. And if you use this system, you can do a proof to figure this out. But with 10 to the 6th possible values, you're not going to have that many potential divisors. Most of the numbers, whatever this is, if this is, for example, 37,248, then this has a limited number of divisors. Obviously, all the prime numbers are not going to work because you're not going to be able to divide it into where everything is prime, or into a prime number of different holding containers. Essentially, what you're doing then is you can say, okay, so as I go through here, is this number divisible by 3? If it's not divisible by 3, then there's no reason to see if you can put them all into 3s because it's not going to come out evenly. Is it divisible by 4? If it doesn't divide by 4, then there's no reason to test that either. So by reducing the number of numbers you have to check, you're reducing the amount of work you have to do. So the way this process then is going to look is you start with your initial list of numbers, you add them all together, and you come up with a total, in this case, 18. Next step is you're going to find out whatever the largest number is, because it can't be anything smaller than the largest number, because if I've got, if I have numbers that are like 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, and then like 50, then there's no reason to see if they're going to add up to 6, because even though I can add these to make 6, 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 50 can't be made into a 6 by adding something to it. So you start with your largest number, and then you just work your way up from there, checking to see, and you can do that with just a while loop, checking to see whether or not your sum of all your numbers is divisible by that. So in this case, 4. 4 is my largest number. So then the question is, okay, would it be even possible to divide 18 falling asleeps into sets of 4? And because 18 modulus 4 is equal to 2, then we know that we would have 2 sleeping periods left over. So there's no way to combine them into 4s. I don't need to check for 4s. Same thing with 5. If I have 18 modulus 5, I've got a value of 3. That also does not come out evenly, which means I don't need to test 5s. If I do 18 modulus 6, 6 is equal to 0, because 18 divides evenly by 6. So that means that 6 is a viable target, which means what I'm trying to do is I'm trying to figure out, is it possible to get these numbers to add up so that everything is equal to 6? If I did, there will be 3 of them, 1, 2, 3, because I know that my total is 18. So then what I need to do is, we mentioned this before, start with your counter. Let me do C for counter. Start with a counter equal to 0. Every time it reaches this target, you reset it back to 0. If it overshoots the target, then you conclude the number is not viable. So we start at 4. So 0 plus 4 equals 4. Move on to the next number. We've got 2. 4 plus 2 equals 6. 6 is our target, so we can start over. Back to 0. Add in 3. 0 plus 3 equals 3. Add in 1. 3 plus 1 equals 4. Add in 2. 4 plus 2 equals 6. 6 is equal to our target, so again, we can start over at 0. Add 4 plus 4 equals 4. Add 1 plus 1 equals 5. Add 1 plus 1 equals 6. 0 and start over. Okay, we've made it through the list. If we are at 0, then that means that our very last number brought us exactly to our target. If this number was not 0, that would mean that it didn't divide out evenly. So even though 18 might be evenly divisible, just based on the arrangement of the numbers, it might not be possible to have them add up to that. For example, if the first two numbers were 4, 3, and then 2, 1, 2, 4, 1, 1, like if I just swapped the order of these two numbers, I wouldn't be able to combine 4 and 3 and get a 6. So in that case, that wouldn't be possible, even though the total is still 18. So you have to check not just what the total is, make sure the total is divisible. You also have to check to make sure that the sequence of numbers doesn't have neighbors that are going to make it impossible to add up to your target. So once we've gone all the way through here, we've verified that it's possible to make everything add up to a 6. We always want to try and keep this number as low as possible, because the lower this number is, that means the more groups we have. If this number gets higher, that means we have fewer groups with more in each group. So if our target is 6, that means we've gotten into 6, 6, and 6. We know how many numbers there are because we've got this 18. So 18 divided by 6 is 3 numbers. And we know how many we started with, which is 1, 2, 3, 4, 5, 6, 7, 8. So if we started with 8 numbers, and we know that we can add them all up to 6, which means in the end we'll end with 3 numbers, then we know the number of modifications we're going to have to do is 5. 5 modifications to get from 8 numbers down to 3 numbers, because again, every time you do a modification, you're combining pairs. So every modification counts down: 8, 7, 6, 5, 4, 3, 2, or 5, 4, 3. Stopping at 3. That's a total of 5 modifications stepping down. So just a real quick recap. Let's go back to the original test set here. Okay, so 1, 2, 3, 1, 1, 1. First step, add all the numbers together. That equals 3, 4, 5, 6, 7, 8, 9. 9 equals 9. Next step is start with the largest number, in this case 3. Then from there, check to make sure that the number here will evenly divide the number here. And if it does, then you have to check to make sure they all add up. And if it doesn't, then you just advance to the next number. In this case would be 4. Testing 3, we have our counter, which starts at 0. Start running through our numbers. Plus 1 equals 1, plus 2 equals 3. That's our target, so we start over at 0. Here's 3, plus 3 equals 3. That's our target, start over at 0. Here's 1, so plus 1 equals 1. Here's another one, plus 1 equals 2. Here's another one, plus 1 equals 3. 3 is our target, start over at 0. We're at the end of the list. This value is equal to 0, which means we successfully completed running through all the numbers, which means that 3 is a viable target. If 3 is a viable target, then that means that the number of numbers we're going to have at the end is going to be the total number of times that she fell asleep divided by the number of times in each group, which in this case is going to be 9 over 3, which is 3. That means that the final is going to be 3 groups, each with a 3 in it. And if I have 9 over 3 equals 3, then I have 1, 2, 3, 4, 5, 6 numbers to start, 3 numbers to end, which is 3 operations. And we can see that that's the answer to the first question. Let's look at the second question, 2, 2, and 3. Once again, we add them all together. 2 plus 2 plus 3 is equal to 7. Our largest number is 3, so we'll start from 3. 7 modulus 3 comes out to 2. That's not equal to 0. 7 modulus 4 is going to come out to 3. 7 modulus 5 is going to come out to 2. 7 modulus 6 comes out to 1. 7 modulus 7 is the first number that comes out to 0. None of these evenly divide 3. 7 modulus 3 is not even. 7 does not evenly divide by 4. 7 does not evenly divide by 5. 7 does not evenly divide by 6. We made it all the way to 7. We didn't even have to run through and look at these numbers in order to know that the only number that can possibly be equal to is 7. 7 divided by 7 is equal to 1, which means we're going to have one number at the end. We can go ahead and run that test anyway. C equals 0 plus 2 equals 2 plus 2 equals 4 plus 3 equals 7. 7's our target, so we start over at 0. We've ended at 0. We verified that 7 is divisible by the number 7. We verified we can run through and make them all add up to 7. So I've got 7 over 7 equals 1. I started with 3 numbers. 3 minus 1 is 2, which means I'm going to have 2 numbers at the end, and that's the answer to the second one. And then just maybe a quick sanity check. If they're all equal, you can just output a 0. We don't have to do any of this work. So that's how you solve the problem. Good luck with it. I will talk to you on the next one.